roughly the size of square root of the discriminant. So I'll write it as discriminant to the power of 1/2 plus little o of 1, some number that goes to 0. Right. Right. That's true. That's true. Yeah, so... Right, right. So in fact, we don't need this equality. All we need is that this number is pretty big. And that was already known to Landau, and then Siegel somehow made it much stronger. So maybe in this case, it's not Brouwer. But I think next time I write it, it'll be Brouwer. Okay. So Brouwer says this. And so as a corollary, I'm not going to claim this for myself. There's nothing written down anywhere. But if you just add these two, the G invariant of E over Q, the size of this degree is of size discriminant of K to the 1/2 plus little o of 1. So K is degree 2 over Q, so somehow these two numbers are off by at most a factor of 2. Okay? And so that proves conjecture 1 sub 1. In fact, sort of plenty of room to spare. All right, so that's the elliptic curve case. So now why do things get messier when you bring in higher dimensional abelian varieties, higher dimension than 1? So now let's let A be sort of a CM abelian variety. And like before, the endomorphism ring of A we're going to assume is just the maximal ring of integers of some K. And the CM type of A is is phi. Just got some CM type phi. Okay, so then we still have a theorem of complex multiplication in this case, but now it's a little bit more complicated. So now we have something called the Shimura reciprocity map. And what it does is the following. You let K star be the reflex field associated to K together with its CM type. So it actually depends on this as well, but it's some other CM field. It's not really a scary object by itself. And then you have this canonical map, I'm going to call it R sub K phi, from the class group of K star to the class group of K. Something you can write down combinatorially just in terms of the Galois theoretic data. And so then the theorem in this case, this is again the theorem, it's called the theorem of complex multiplication. One incarnation of it is that, so I'm gonna mess this up if someone wants to correct me, but last I checked, what you do is you look at the field definition of A adjoint K, and this will contain K star, in fact. And then if you look at this Galois group, then this is isomorphic to the image of R sub, what did I call it, K phi. All right? I'm not entirely sure if it's a K star or a K here, but for my purposes, I don't really care, because I only care about the size of this number. But I think this is right. Okay? All right, so why is this harder? Well, now to show that this number is big, which is really all we care about, that the size of this group is big, all we need to show is the size of the image of this map is big. And Brouwer and Siegel tell us how big both of these guys are, but the problem is that understanding images between class groups is much harder than understanding sizes of class groups on their own. And let me explain why, but first let me just point out that in the G equals 1 case, K star turns out to equal K, and this map, as you might have guessed, is just the identity map. So in this case, the image is the whole thing, which is why it was so much easier in the case of G equals 1. So let me erase this, and let me explain somehow the fundamental difficulty that comes up in this images between class groups problem. And so here's sort of a hypothetical example. What you can imagine showing up there is that the reciprocity map, so in this example, K equals K star, and the reciprocity map is just the multiplication by M map from the class group of K to itself. Somehow it's, this is in some sense the simplest you could hope for it to be. So in this case, the size of the image, of the multiplication by M map is, using group theory, the size of the entire class group divided by the size of the M torsion in the class group. And it turns out that bounding M torsion in class groups is extremely difficult. So this is a problem about which we know sort of almost absolutely nothing. Only in extremely low degree cases can we provide somehow some sort of non-trivial bounds. So to illustrate just how little we know about this problem, which I think is very interesting, there's a conjecture of Shou Zheng, sort of a folklore conjecture, but he wrote it down, which says the following. I think it was 2006, right? 2006? Oh, okay. Well then, I can write anything I want. 2004, which says the following. So fix M and N, and let K just be a field of degree N over Q. Then if you look at the size of the M torsion in K, then this grows subpolynomially in the discriminant of K. Okay, so we somehow expect very, very little torsion. And so by the Brouwer-Siegel theorem, this is certainly at most the size of square root of a discriminant, because this is the size of the entire class group. Okay, so it's somehow extremely open to get, I guess you could call it a subconvex bound in this case, to just put 1/2 minus a tiny amount here. Only in the case, I think, where sort of M is 2 and N is at most 4, or M is 3 and N is 2, can we provide any bounds whatsoever, otherwise it's completely open. All right? But so, if you could resolve this difficulty, if you could prove Zheng's conjecture, or even much less than Zheng's conjecture, somehow some non-trivial saving, then you could resolve this conjecture quite easily, it turns out. That's the main obstruction to understanding this. Okay, but we can't. So that's why this is hard. All right, so now let me talk about the conjecture of Kolmez and how it plays a role. So let me say a few words about Falting's height. So this was invented by Falting in order to prove his big theorem, the Mordell conjecture, one of his big theorems. And what it is a measure of arithmetic complexity to abelian varieties that are defined with the evaluate it and take a look. How's the size of the volume of A? All right. Okay, so it should not be immediately clear this has any properties whatsoever. But in fact, it turns out to be a very good function. It behaves like a height function should. So if you fix the field K, there's finitely many abelian varieties under a given height. And if you take a height on the moduli space, it's very similar to the Falting's height. So it's a very good canonical height function. You can define the abelian varieties. Right, so because it's a precise height function and not just something defined up to a constant like Lie heights usually are, you can hope there are some nice formulas to go around. And so there's a beautiful conjecture due to Kolmez, which says the following thing, that suppose A has CM type K phi, and the endomorphisms of A are the full ring of integers. He actually insists on this in this case. I presume you can get a formula in any way, but in any case, but his formula, his conjecture is written down, has this condition inside it. Then the Falting's height of A is equal to the following thing. You take a sum over irreducible representations rho from the Galois group of the normal closure of K over Q to some GONC. You sum over all irreducible representations. And now you have some rational constants, C rho phi, which depend only on the combinatorial data involved, not on the actual field, just the group G together with combinatorial data of phi, multiplied by the logarithmic derivative of the L function at 1 plus the log of the Artin conductor of rho. Just to GONC is what I wrote. This is K norm, the normal closure of K. Because K might not be Galois. Just the normal closure. That's right. Okay, so we're not really relevant to us, but these are numbers that are rational and somehow only depend on combinatorial data. Okay, so this is a beautiful conjecture, and let me write down a sort of immediate corollary of it once you know what modern analytic number theory already knows. And the corollary is that if you look at the Falting's height of this abelian variety, I'll write it in absolute value, but in fact Falting's height can't get too small, then this grows subpolynomially in the descriptive. So it's kind of funny. And we're only going to use this in this very sort of perverse, light-hearted way. But without this formula, I'm hard-pressed to give you any bound whatsoever. So I used to say that I can't give any bound. In fact, I was wondering whether I could probably give exponential bounds. I think it's a thing. That's right. But their main theorem of classrooms amounts to is a slower block. Steve, you've been known for a while what it is. It has to be Steve. Right. Absolutely. There are certain a single Galois orbit. In general, that's very much not true. They can split up into lots of Galois orbits. And even though the size of the Galois orbits we're trying to get at, that's kind of subtle, the size of S is actually pretty straightforward. So this is up to constants. Equals, I'm not quite sure what the constants are. But the size of this is the size of the class group of K divided by the size of the class group of the totally real subfield. Okay? And again, using Brouwer-Siegel, that happens everywhere, this is at least of size discriminant to the 1 coordinate. Okay, so regardless of what's what, if you give me a CM type, then I can give you lots of abelian varieties that are principally polarized of that CM type. So they exist without much fuss. Okay? And here. So if A and B are in S, then A and B are isogeny.
をお取りください。整理券をお取りください。整理券をお取りください。
points behavior. So a simple example is the following, okay? Let me say this. In the family z squared plus c, you can tell whether or not simply by considering the orbit of 0. If the orbit of 0, which is the critical point in this family, if the orbit of 0 is bounded under iteration, the Julia set will be connected. If it's not bounded under iteration, the Julia set will not be connected. Okay? Oh, critical, I really just mean ramified. So it maps to its image with degree